Hello from Group 28. We are Cassandra Young and Sim Shu Fen. We are presenting about the numerical method projects on the Runge Kutta methods. So the Runge Kutta method can be represented in the general forms of equations, whereby the phi is the increment functions. So the phi can be obtaining from the products of a terms, which is the constant, and the k terms. So we are taking the second order versions as the example, so we can obtain the k1 from the ordinary differential equations and the k2 from these ordinary differential equations. So in Kalagirathu paper dated in 2013, the author claimed that where the initial value problem y prime can be represented in this form of the ordinary differential equation, and the y naught x naught equal to I naught is the initial value holds. So the x stage of the Runge Kutta method is determined by the triplet C, A, and B. So we continue with the derivations of the second order Runge Kutta methods, where this is the general forms of the equations, and k1 we substitute inside the general equations, which k1 is obtaining from the previous slide, and the k2 we obtaining from this ordinary differential equations, and we are comparing with the Taylor series after expand. We substitute inside the general forms of equation. From the substitutions, we are obtaining these equations with the truncation errors. So we are doing our research paper is about the constructions of an optimized explicit Runge Kutta Nystrom methods for the numerical solutions of the oscillatory initial value problems, where the abstract we discuss in this slide. So based on the research paper, this paper construct an explicit Runge Kutta Nystrom method with 4 stages and 5th algebraic order. So this method has variable coefficient with 0 phase lag, 0 amplification factors, and 0 first derivative of the amplification factor. So this paper provides an analysis of the local truncation error. So in this paper, we are comparing the new method to some constructed optimized methods to measure the efficiency of the method. So in Simmons, Costi, and Anastasi paper dated in 2011, the author claimed that it approached the solutions of the second order equations where the y prime prime t can be represented in this form of ordinary differential equation, where the following y x naught equal y naught, y prime x naught equal to y prime naught is where the initial condition holds. So we continue with another research paper in B. Paternoster paper dated in 1998. The author claimed that where the initial value problem also can be represented as this ordinary equation, and so we consider the second order of y prime prime t, where we can represented in this ordinary differential equations. We continue with the explicit Runge Kutta Nystrom methods, where it says that Runge Kutta Nystrom method has algebraic order p if the new value minus the old value is equal to the truncation errors. So the h is the step size, where the p is the orders of the algebraic equations, and where the first order equations can be represented in these equations, where the new value minus the old value is equal to the local truncation errors, where p also the order of the ordinary equations. So we continue with
So now we'll be talking about the phase lag and amplification factor analysis of the Runge Kutta method. So this is the phase lag, which is the difference of V and T. If the phase lag is the truncation error, then the method is said to be a phase lag order Q. As could be seen, this is the truncation error with the order Q. Similarly, for the amplification factor, it is a difference of 1 minus the modulus of rho. So if we say that this is a truncation error, then the method is said to be an amplification factor order R. So in this research paper by Simoskowski and Anastasis, the authors claim that the Runge Kutta method has an algebraic order P if the difference, which is the difference of the new value minus the old value, is the truncation error. So similarly for the phase lag, there's a difference. So this, which is the phase lag, will be equal to the truncation error as well. And for the amplification factor, 1 minus the modulus of rho, it will be the amplification factor order R. And in Cilios and Simon's paper dated in 2005, the authors claim that the Runge Kutta method defined where dissipative or of order P of the difference of these two terms is the truncation error. So this fact is also claiming about the truncation errors. So now we'll look at the construction of the new Runge Kutta method, which is the main focus on our research paper. So to produce the new method with variable coefficients, they were set free B1, B2, and B3. So the variable coefficients were the phase lag, the amplification factor, and a derivative amplification factor. Seeing that there's B3, B2, and B1 in the equation. So the author has used B1, B2, B3 equations, and through the substitution of these three coefficients, we are able to eliminate it, and that's the meaning of set free B1, B2, and B3 terms. And for error analysis, in order to verify the order of the new constructed method, we study its local truncation error. So LTE here stands for the local truncation error, and it is a difference of the new value and the old value. So differences gives the local truncation error. So the one below is the new method's local truncation error. Shows that this method is the order of this method is 5. So this can be seen because the coefficients up to the power of h to the power of 5 has vanished. So it can be seen here the smallest order is h to the power of 6. So 6 can be obtained because of number of terms plus 1. Number of turns here is 5, so 5 plus 1 equals to 6. So in this paper, they use 4 problems to analyze the accuracy of the various methods. The first problem is the two-body problem. And it can be seen that is a theoretical solution. And there's a graph showing the analysis of the different method. And it can be seen that the new method has the highest accuracy. And for the second problem, which is inhomogeneous problem, the graph also shows that the highest accuracy belongs to the new method. And for the third problem, Duffing problem, with the theoretical solution below, the graph clearly shows that the new method, which is the green line, has the highest accuracy. The fourth, which is the final problem, is nonlinear problem. From the graph, it can be seen that once again, the new method has the highest accuracy. So the conclusion of our research paper is this picture is obtained from the research paper. So from this conclusion and the first sentence, we can know that a new method based on the Runge Kutta method is constructed. And from this sentence, we presented the analysis of the local truncation error, we know that the analysis has been done on the local truncation error. Last but not least, the efficiency of the new method has been tested, which can be seen from the 4 graphs previously, and the paper concluded that the new method is the most efficient among all methods being tested. So this citation has shown us that the efficiency of a method depends on its cost, usually the number of stages, and how large the truncation error term is. So it's defined that the effective error, EF, of a method, taking into account the number of stages and the size of the truncation error. So due to the from this research paper, it analyzed on the truncation error and therefore minimize the effective error EF, resulting in the new method being the most accurate than the other methods. So that is all from our slide. We hope you enjoy our slide. Thank you.